So the topic today is that I have. I think the morning sessions are really interesting, and a lot of theoretical as well as practical aspects. What I'll try to do is to go a little bit more from system side and see how that flow into the silicon, and that would be kind of the topic in this session. So before we start, I'd like to really acknowledge some of the people who really contributed a lot in this work. The folks from Sci-Fi, some of the guys, Henry Cook, Christy, Howard, and some of my colleagues from IDT contributed for this work. So one of the things that we in the industry are saying, as all of you have probably been noticing, that the data growth is really driving the internet. And some of the data that we look at is this massive growth from the social media, which is changing not only the entire network, but also the infrastructure that sits in the core of the network. Some of these YouTube upload videos, and this video that's so interesting that 800 million people watched it. Only 642 million went to Disneyland since 1955. The key point that I wanted to say was that if you look at some of those data, all those data is actually unstructured data. Very hard to find structured data nowadays, and a lot of these data don't include the machine data that's coming up. As part of the company that I work for, we have this luxury that we kind of sit in the edge of the network in the wireless systems as well as the sensors. And what we see is that there is this massive real-time usage increasing. There is significant amount of data coming from the access network, and that's going to the core. And it's important that the data centers actually try to keep up with this massive influx of data that's coming from everybody, all the users. The other aspect is that if you want to really make some decisions based on those data, you have to react really fast. You need low latency response times. Some of the use cases that we try to focus on in robotics, wireless access network, space and military, and HPC and analytics. The most important ones that I like to talk about today are related to real-time video image recognitions, some of the network signal processing and analytics there for some of the future space missions that we have been looking into, some of the Mars mission that's coming up in the 2020s that we have collaborated with NASA. Some of those require very fast image and video processing. And then in the HPC analytics, you have the performance critical data analytics. But as we see this kind of analytics, the underlying structure seems to demand that you have, you need number of nodes to process, where the nodes will have some memory attached to it, and then you will also probably have some storage with it. But you just can't really do that with just few nodes. You need actually many, many nodes. But not only that, you actually need a very deep net. You have to have many, many nodes. You have to push the data through it, and you have to let them recognize that. So if you look at all of these analytics, many of those seem to be able to take advantage of this underlying structure. A lot of you know about this, seen this semantics already many times. One of the critical things we have seen is that to make such network really work very well, you need to have a balanced low latency computing, but also the processing has to match with the I/O memory and storage processing bandwidth and the performance. If the CPU nodes or the accelerator nodes are very fast, but if it cannot access the memories fast enough or the storage fast enough, the overall processing time actually crawls down. So now, that's kind of the use case perspective. But if we look into the network evolution, so we are now leaving the box and going at the network level, and we're looking into some of the statistics. So if you look into the wireless network, it's actually the data rate is significantly accelerating in terms of how much data rate that you're going to see from the 2G, 3G to 4G, LTE, 300 megabit to gigabit, and now in 5G, we're approaching around 10 gigabit that people are trying to get in your user devices. The most important part is that not only that the bandwidth is actually increasing, but the latency from the second generation network, as you go to 4G and 5G, the latency from 150 millisecond is down to 1 millisecond for the round trip. So from the time that you look for some data on your web interface to the time that you get the results back is going down significantly. And that's to actually keep up with so much data and the insight that you want to get. So you have to make some kind of decisions within that time and get back to the user. So what's happening is that if you look into the network, as a user, we push the data through, goes through the radio, goes through the base station, which is at the edge of the network. And it goes into the core network through the gateway and eventually to the servers and storage. To keep up with that bandwidth and round-trip latency, one of the biggest trends that's happening is that some of the servers and storage is actually collapsing towards the base station. And some of the gateway functions is also collapsing there, so that your round-trip time could be actually coming from the edge of the network. The other critical advantage is that if you do that, the bandwidth that you need to push to the core actually drops significantly. There are quite a bit of research studies done. If you look into Google, you see that some people claim you can almost reduce 50% of the data. So, and that has a tremendous implication, because you don't really have to always run the core network at significantly higher throughput. So we always don't have to say, hey, the core network I/O has to go up significantly because we are getting so much data. You could actually intelligently terminate some of the traffic right at the edge. And if you do that, then your computing kind of goes into the edge of the network. Then you have a different type of problem to coordinate those distributed computing. So in terms of the network level, what's happening is that you have all these mobile users in the self-driving cars going to the base stations, and then terminated across the network. And some part of this is going to the core, and a lot of those in the servers. So that's kind of a network view. So now if you come back to the computing model, so we could reduce some of the bottleneck into the computing model by distributing some of the computing and storage resources at the edge. But if you go to the computing model, one of the critical things we have seen is that because the CPU is getting faster and faster, but not necessarily the memory and the storage, and the I/O is not keeping up, you still have that challenge in terms of the matching performance, both in terms of latency and throughput. So this is, if you open any x86 servers today, you're going to see similar problem. If you have an accelerator like a GPU, you're going to see the same problem. GPUs are pretty fast, but cannot get enough data to actually process it, so it's sitting idle. So what we did is that because we are sitting at the edge of the network, and we have seen the computing architecture there was very efficient in that, as opposed to the traditional server network where you have an external I/O, a lot of those I/O processings are already integrated, and you can significantly reduce the overall round-trip latency. So we said, OK, can we bring that model into these servers, because these are pushed into the edge of the network. And if we did that, then what happens is a lot of those computings have an integrated NIC, and your latency goes in the range of around below a microsecond, as opposed to tens of microseconds. And if you have the servers located, then you can do the analytics and processing right at the edge, reduce the amount of data that will go to the core while you process your signal processing and the network at the base station. And you can cluster them with a very low latency switching. So, so that was kind of like the theory. I said, OK, now what happens if you go into the real scenario? So went ahead and opened a Dell computer. And when you open the Dell computer, we see the Intel x86 motherboard with the memories and stuff. But then we have the problem with this I/O and the memory matching. So we took everything out from that computer and took NVIDIA GPU evaluation cards. We stacked 4 of them inside that. The only thing we remain is the power supply. And then we put 4 NIC in there. These NICs actually matches the bandwidth required for the GPU processing. There are 192 CUDA cores in there. So we can very nicely balance the I/O with the GPU performance. And then we have the SSDs connected from these GPUs. So once we build that, then we said, OK, this looks very interesting. But how do you actually scale this thing? Because we cannot put on these big PCs. Fortunately, based on this work, we did some use cases that I'll show you very soon. One company came and said, hey, I can take this whole computer, and there is a switch box actually outside. I can take the whole thing and put into one single card, which is you can take that card and you can put like between 4 to 8 of those cards in a 19-inch server. So you get from 4 GPU evaluation cards, which has matching I/O, but because of the evaluation card, your throughput is very limited, like around 2 gigabit. You can actually put them here, and you can create 56 gig I/O throughput and still get a significant performance boost. And you can then cluster all of those into a 19-inch rack with a 38U system, get 144 teraflops. This is just traditional NVIDIA Tegra K1 GPU. Very powerful, very nicely balanced I/O. And you can scale that system. So you can continuously scale out because the I/O will actually let you balance the traffic. And that was all good. So to show you, once we build that prototype, we went ahead and actually ran a real-time video analytics on that system. This is a computer that was hacked from the Intel, moved into a low-power GPU and ARM. This one is running now actual video processing on that PC box. Very simple algorithm to identify if there is a vehicle or not. The architecture is extremely simple. Use 4 GPU with the Rapidio switch and a NIC. And this one is running a deep neural net. And we are basically recognizing images, running the very familiar from the Berkeley CUDA course. And this is the production hardware. And we are getting very good result, actually. So for the video, we are getting 29 frames per second per node. And the maximum power that we were seeing was approximately anywhere between 5 to 11 watt, depending on how much loading you did for each node. And the images that we were processing were around 6 milliseconds per image. At the time, the best image at the time was around 4 milliseconds. But that was if you went to a very high power GPU, like around, say, 240 watt GPU with an Intel x86. The GPU had a lot of processing capability. The problem was it was not able to push enough images into it. So we took that architecture and also collaborated with NASA for the future Mars mission, where they're looking into for the space shuttle, when it is actually landing on the Mars, it doesn't know the landing site. So what it has to do is, in real time, take the 4K video stream, and when it is decelerating, it has to find the landing site. So it has to process video very fast and make a decision where should it land. And we applied the same architecture and got very tremendous result there as well. So with that architecture, one of the critical advantages that we got is we could get a shared memory model. The CPU and the GPU could share the same memory, so we didn't have to leave the GPU. So that was a tremendous advantage. So the GPU and the ARM was in the same processing unit. And we like to take that learning from that. But one of the critical problems that we had was we still needed the external NIC, because the GPU had the PCIe port, which does not provide a scale-out architecture. So we had to use an external conversion for a to create a peer-to-peer network. So then the idea of RISC-V came in picture. We still had the switching fabric 100 nanosecond, but we were limited by the NIC capability. So we took that architecture and we said, OK, if we need memories and storage here, how do we create a custom processor? How would the processor look like if we did actually build it? If we had the NVIDIA GPU but with integrated I/O, what it would look like? And that's when the RISC-V came into play. And we said, OK, if we take that memory, CPU, storage architecture and map it, so what we would want is number of different core and number of different accelerator, potential and integrated NIC, and have a switching fabric so that we can create these neural networks, and the storage would be a pool of memories. So from that, the idea is, OK, how do we get the cores and the fabric as a first-class citizen on the CPU? So we had two options. When you look into the existing RISC-V, there are two options. You can actually connect the fabric from the AMBA AXI. So there is already AXI bus. You can hook up your I/O. You're good. But you are in the kind of like in the second-class or third-class citizen in the CPU at that point. The other option you have is the Tilelink, which is actually the first-class fabric in the RISC-V. So our thought was, OK, so the AMBA ARM, you can actually do it. There is a spec available today for large shared coherent clustering. It's at 0.75 release with the AMBA AXI and Rapidio. And the Tilelink gives you the first-class citizen capability. So we took the Tilelink, very, very efficient interconnect for on-chip. How do we take that and go off-chip? So the concept there is, OK, take a rocket generator, go into the L1 bus, and do a memory map. And from the memory map, run a messaging as well as Rapidio fabric, put out an external switch fabric, and create a shared coherent memory model. You still have the AXI option if you wanted, so you could actually push some of this fabric here. We wanted to get into the first-class level so that we can reduce the round-trip latency significantly. So the concept looks good. The next step was, right now, as of last 2 weeks, we got a new branch from the RISC-V generator where the single CPU with this memory map I/O with a port available for the Rapidio. So anybody can actually take that branch, and you can integrate the Rapidio IP. And then this switch already exists commercially, so you can actually create a cluster. So we said, OK, let's take that generated core and see if we can create a split simulator to validate some of the concepts. So the first thing you do is say, OK, how do we communicate off-chip? How do we send my information to the other CPU? Set up a packet structure. So the idea would be SoC1, one of the rocket chip, will notify the SoC2 about its intent to read some data from a memory that's hooked up to this SoC. The data could also be a storage. This SoC2 is going to check the lock on that memory or the storage space, notify any other SoC who is using that. Those guys will respond back, and eventually SoC2 is going to release the ownership so that SoC1 can get the data. To reduce latency, you can also let the third SoC actually send some data back. So very simple model, traditional coherent model. But it allows you to do a peer-to-peer response, not like traditional x86-based PCIe root topology. So there is no root. There is no host, single host system. It's a peer-to-peer network. So we took the Tilelink messaging structure, 5 different type of transactions, and we have now the initial packet structure available. So this is very much in a draft stage at this point. So we are welcoming the community to actually start looking into that, contribute to make it improved and optimized. But this is our baseline structure. So the way it happens is that every packet has some form of acknowledgement. So you send the packet, the remote node is going to acknowledge that he got the packet, otherwise you retry. You have some kind of F-type, so you say what type of packet you're sending. It's all based on destination ID-based routing. So it's a fully packet-based network. You put the destination ID, ship from a particular node. The switch is going to find out where it is going to go based on the destination ID. and you keep the source ID so that you can get the response back. And the payloads are basically various sizes, very granular, starting from 1 byte all the way up to 1K if you need. CRC protected. So we finished our first simulation. What we're estimating is that, so this was just a basic 2-node system going from integrated node 1 to node 2, ingress and egress, and we're speculating that the performance that we're going to see is in the range of 100 to 200 nanoseconds. So this is like, we're talking about anywhere between 20 to 30 clock cycles. So I wanted to end my talk actually with this. The main idea that we are talking about is that you could actually reduce your overall data bandwidth bottleneck by distributing your compute at the edge. So if you take a macro level, that's what you would do. And then when you go into the edge of the network and you look into the computing architecture, you could potentially create very efficient accelerator-based processor by integrating the I/O and bring the I/O at the first-class citizen and give it the I/O and memory expansion capability so that you can solve some of the analytics problem that we're seeing now.
Thanks, Mohammad. Couple of minutes for questions for Mohammad.
Hi, I'm a guy from Mellanox. Just a question. You said that it's kind of a coherent scale-out architecture. I mean, do you have like cache coherency over all this structure, or this is just a method of accessing remote memory without coherency?
So this particular architecture supports two semantics. You can have a completely coherent network. So you may have, say, 16 processor with accelerators. They can be all a coherent group. If you wanted non-coherent communication, you can also support that because the Tilelink baseline actually support the messaging without any kind of coherency. So it supports both coherent and non-coherent transactions.
So coherent in the sense of from L1 all the way across all the system?
That's right. So the first stage that we are doing right now is that the coherency is going to be from L2 onwards. And the way we are expanding it is that it's going to be L4 at this switch level. So if you go back to this diagram here, this would be an L4 coherent shared network. Whereas if you're inside here, this would be L2 coherency.
To build a coherent network, don't you need some virtual network support or something, right? I mean, you have to be able to support packets of request and response packets or something like that.
Right.
So does the Berkeley implementation already provide that, or you are imposing it on top of it?
So, so currently there are two schemes available. So we'll go through this one. So basically, if you do simple MSI or MOSI-based schemes, the Tilelink actually has, if you're doing non-coherent, so that already has simple request-response pair. If you're doing coherency-based, it has actually on top of that, you can define, it's already defined where you have not only request-response, but you have invalidate, cache invalidate, cache grant, cache line access.
Yeah, it's not the. Oh, they are different networks.
That's the 5 priority levels.
Ah, okay, got it.
Separately, yeah.
Yeah, that's the answer.
Yep. And then there are also, the secondary scheme is that the fabric itself, this fabric itself has also a coherency scheme with the 8 priority levels separately. So if you need to utilize that, you can also do that.
Just one more. Why is it over Rapidio and not over some other thing like Ethernet or that is more scalable? What's the benefit there in Rapidio versus other interconnects?
So you could use Ethernet. The first problem that you will face is the protection in terms of reliability of it. So if you want to get a reliable Ethernet network, so if you want to build a coherent network and interchip communication, you want to have a reliable link. If you use Ethernet, one of the first problems that you have to solve is how do you make it reliable. So
we have like Rocky, all this type of thing.
Right. So if you do Rocky, then what happens is your overall latency starts going up significantly. Whereas in the Rapidio case, we can almost guarantee that if you do a peer-to-peer network like node to node, you could be within 80 nanoseconds. whereas if you're going rocky, you're going at a microsecond level latency. So then, and so therefore, from the software perspective, if you want to build a coherent shared network, then you can no longer be a first stage memory. You have to be kind of like disk drives kind of thing. So you can't really build a very fast analytics framework using traditional Ethernet type semantics. Yeah, so that's the main reason. The other thing is this kind of architecture already, so this embedded type architecture already actually has significant, it's already proven in the network, like here. So this is already deployed in millions in the wireless network. So if you make a phone call today in 4G base station, this architecture already exists. So the part that we are bringing in is just the servers and the data analytics. That's where the RISC-V 64-bit processor with accelerator come in play. So this embedded NIC already exists. It's available. And so that brings the advantage of the embedded to the server space.
Thank you. Alexander Sintakor. So can you tell us about your company plans about deploying this thing? Is it like exploratory project, or is it something you are considering like for production?
Okay.
Thank you.
So this particular part here, so to answer your questions, we are very, very interested in this particular path we are on. So we are really looking forward to, so this is already available. So we together with the collaborators we have, there is a port available now with RISC-V for this I/O map. So what we see is that, and the packet structures are, baseline packet structures are defined for the request response with their priorities and flow control. So what we are looking for the community is to actually join as an I/O and memory working group and actually build a proper framework and the specification for it so that we can put into an FPGA. So the next step would be to, so the RTL is available, we need to put into an FPGA, start doing emulation while we define the spec for the I/O and memory scale out. So yeah, we are very, very interested, and if any of you are interested, please contact me or any of the collaborators.
Great. Thanks, Mohammad.
Thank you.